Hello everyone. Today I am going to present the topic curved lines, surfaces, quadratic surfaces, and blobby objects, which is an important part of computer graphics and vision. These concepts help us create realistic models of objects that are difficult to represent using straight lines or simple geometric shapes. Throughout this presentation, we will understand how curves and surfaces are represented mathematically, how quadratic surfaces are used in graphics, and finally, how blobby objects help create smooth organic models. In today's presentation, we will discuss four major topics. First, we will learn about curved lines and curved surfaces. Next, we will understand different methods used to represent surface. Then, we will study quadratic surfaces and their different types. Finally, we will explore blobby objects, their mathematical concept, applications, advantages, and limitations. Now, let's begin with the curved lines. Unlike straight lines, curved lines continuously change their direction. They are widely used in computer graphics to create smooth and natural looking objects. Curves are essential for modeling circles, vehicle bodies, character animation, forms, and free form designs. There are several important types of curves used in computer graphics. The first type is the Bezier curve. Bezier curves are defined using control points. The curve always starts at the first control point and ends at the last one. The intermediate control points influences the overall shape without necessarily lying on the curve. The second type is B-spline curve. Unlike Bezier curves, B-splines provide local control. This means moving one control point affects only a small portion of the curve rather than the entire curve. The third type is Hermite curve. Hermite curves are defined using two endpoints and their tangent vectors. These tangent vectors determine how the curve enters and leaves at each point. And finally, we have parametric curves. Instead of expressing y as a function of x, both x and y are represented using a parameter, usually denoted by t. Parametric curves provide greater flexibility and can represent circles, loops, and many other complex shapes. Now let's understand parametric representation. Instead of writing a curve as y equals f of x, we represent it using two separate equations. One equation defines the x coordinate, while another defines the y coordinate, both depending on a parameter t. As the value t changes, the point moves along the curve. There are several advantages to this approach. First, it naturally represents motion because increasing t traces the path continuously. And second, it can represent curves that cannot be expressed using ordinary functions such as circles and vertical lines. Third, extending to three dimensions is very simple by just introducing another equation for z. For these reasons, almost all modern graphic systems represent curves parametrically. This slide shows an example of a parametric curve. As the parameter t changes with a specified interval, the x and y coordinate change simultaneously. Instead of thinking about the equation itself, it is easier to imagine a point moving smoothly along the path as time progresses. This representation forms the mathematical foundation for animation, paths, and computer generated curves. Now let's move to the next slide. Now, curved surface. Curved surfaces are created by extending curved lines into three-dimensional space. Examples include spheres, cylinders, torus shapes, and freeform surfaces. These surfaces are used extensively in animation, gaming, industrial design, product visualization, and medical imaging. Curved surfaces allow computers to model smooth objects instead of representing everything using flat polygons. There are several methods used to represent curved surfaces. One method is parametric surfaces, where two independent parameters define every point on the surface. Another method is Bezier surface, which extend Bezier curves into two dimensions. Finally, B-spline surfaces provide better local control, allowing designers to modify one region without affecting the entire surface. These techniques are widely used in CAD software and animation. Now let's discuss these examples one by one. A parametric surface uses two parameters instead of one. You can think of it as moving in two independent directions over a surface. Every point on the surface is calculated using mathematical equation, and this method is commonly used for creating complex three-dimensional models. For example, we can see here grid lines. If you hold mu constant and vary v, you get a curve. By doing this for many values of u and v, you create a wireframe grid or isoparametric curves. And the examples are also given here using angles theta and phi. Now let's move on to the next type. So yeah, Bezier surfaces are created by extending Bezier curves into two dimensions. A grid of control points determines the surface shape. Moving one control point changes the overall surface. These surfaces are commonly used for designing smooth product models and animated characters. The formula is it uses the Bernstein polynomials as blending functions. The formula is given below, which we have to use to calculate the Bezier surface. B-spline surfaces improve upon Bezier surfaces by providing local control. Moving one control point affects only a nearby region. This makes them ideal for designing complicated engineering objects such as aircraft wings and automobile body. Modern modern CAD systems often use NURBS NURBS or non-uniform rational B-splines because they can accurately represent circles and other precise engineering shapes. Let's move on to the next topic, which is quadratic surfaces. What is a quadratic surface? Quadratic surfaces are surfaces defined by second degree polynomial equation in three variables. The general equation for quadratic surface is given below, which is ax squared plus by squared plus cz squared plus dxy plus eyz plus fzx plus gx plus hy plus iz plus j equal to 0. As we can see here in this equation, this is a second degree polynomial equation. So this is the general equation for quadratic surfaces. Quadratic surfaces are three-dimensional surfaces represented by second degree polynomial equations involving x, y, and z. Many common geometric objects belong to this category. Examples include spheres, ellipsoids, cylinders, cones, paraboloids, and hyperboloids. These surfaces appear frequently in engineering architecture and also scientific visualization. Now, let's move on. Yeah, next. Now, in this slide, it introduces different quadratic surfaces and their real life applications. Ellipsoids are used to model planets and bounding volumes. Hyperboloids are commonly seen in cooling towers and modern architecture. Paraboloids are used in satellite dishes, telescopes, and reflector mirrors because they efficiently focus signals and light. Cones and cylinders appear in countless engineering structures, and these mathematical surfaces help computers generate realistic three-dimensional objects. So as you can see, there are some real-life examples of ellipsoid, cone, sphere, and cylinder, hyperboloids, and paraboloids. An ellipsoid is a generalized form of a sphere with three different radii. In computer graphics, ellipsoids are often used as bounding volumes for collision detection. Hyperboloids, and if we talk about hyperboloids in the next slide, hyperboloids exist in two forms. A one sheet hyperboloid resembles a cooling tower, and a two sheet hyperboloid appears as two separate curved surfaces. So, these shapes are commonly used in architecture due to their strength and unique appearance. As you can see in these images, will show the one sheet and two sheets, and these are the formulas given here for these two types. If you move on, there are two important paraboloids. The first is elliptical paraboloid, which resembles a bowl. The second is the hyperbolic paraboloid, commonly known as the saddle surface. Despite its curved appearance, the saddle surface can be constructed using straight beams, making it popular in architectural design. And paraboloids are also widely used in satellite antennas and reflector systems. Now let's discuss blobby objects, also called as metaballs. These are smooth organic shapes that merge together naturally. Each object creates a field of influence around itself. When two objects come close, their fields overlap and merge, producing one continuous surface. This creates realistic liquid light and soft body effects. Blobby objects are widely used in character animations, water simulations, molecular visualizations, and special effects in the movies. The mathematical idea behind blobby object is based on field values. Every point in space has a field value generated by nearby metaballs. Whenever the combined field value exceeds a certain threshold, the surface is generated. This allows objects to merge smoothly without visible gaps. The formula is given here, and some important characteristics are also there, which include smooth surfaces, natural deformation, realistic merging, and fluid-like motion. Now, blobby objects have many practical applications, and they are used in character modeling, liquid simulations, molecular visualizations, medical imaging, and etc. Their biggest advantage is their ability to produce smooth and realistic organic shapes. However, they also have some disadvantages, which are like generating metaballs requires significant computation, makes them more expensive than the ordinary polygon. To conclude, curved lines and curved surfaces help us model smooth and realistic objects, and their types help us to represent these curves efficiently. And together, all these concepts that we have studied play an important role in modern computer graphics, animation, and 3D systems. Thank you for listening.